Hi, this is Algebra 1, Module 6, Lesson 2, I rule. We're going to solidify kind of this idea of finding the patterns. Marco has started a new blog about sports at Imagination High School. Mascot is the Fighting Unicorns, that he has decided to call iSite. He has created a logo for the site website that looks like this. He's working on creating a logo in various sizes to be placed on different pages on the website. He's developed the following designs. So size 1, size 2, size 3, size 4. Okay, so if I'm going through here, size 1 has 7, 2 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, so how many squares will be needed to create the size 100 logo? Well, that's a pretty big jump. So let's jump to 2 and say let's develop a mathematical model for the number of squares in the logo. So I'm going to go ahead and do a little bit of a table down here. So my first one has 7, second one has 12, third one has 17, fourth one has 22. If I'm looking for patterns, that's a plus 5. So that means this one would be 27 for my fifth one, which means I should have what kind of graph? If we have a common difference of 5, that means this should be a line, right? One would be 7, 12, and we're just going in a line like this. So we should make a line out of this one. All right, so knowing this, let's go ahead and do my recursive. So f of 1 equals 7. And each time f of n is f of n minus 1, my last one, plus 5. Which means then when I'm going to make my explicit equation, f of n equals 5 is repeating, and I start with 7. So it's 5n plus 7. So to get the 100th, I'm going to take 5 times 100 plus 7. Oh, wait, n minus 1. Let me take that back. Give me a second here. Because I'm starting with my first term plus 7. There we go. All right. So 5 times 100 minus 1 plus 7. So 5 times 99 is 495 plus 7 equals 502. Because we know it's got to end in a 7 or a 2, right? And so there's all my equations. Those are types of patterns we've done before. There was just a visual to go with it. No worries. Okay, so now he decides to experiment with making his logo blockier so that it looks stronger. So now his first one still has 7, but his second one has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. It's 28, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, so now we've got 3, 6, 9, 12. 3, 6, 9, 12, 15, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 times 3 is 63. Okay, this is getting big fast, isn't it? So, assuming he continues with his pattern, we need to find the one for size 4. Well, Size 1 had 1 block. Size 2 had 2 blocks. 3 has 3. So 4 is going to be 1, 2, 3, 4. And as it goes in, yep, 1, 2, 3, 4 down, 1, 2, 3, 4 across, 1, 2, 3, 4 down, 4 across, 2, 3, 4 down, a whole bunch across. Let's see, we have 4. Should be another chunk of 4 in there, right? 1, 2, 3, 4. And then another chunk of 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I should be able to go 4 across back in. I still have 4 in the center. A little tricky. Okay, so it should look something like that. And find the number of blocks. Well, we said it was 4 times 12, 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 24, 25, 26, 27, 28. So 4 times 28 would be 112. All right. So what's it asking for next? Develop a mathematical model for the number of blocks in the logo of this size. Okay. Well, I'm going to go ahead and do my table here and see if I notice anything. So 1 was 7. 2 was 28. 2 was 28. 3 was 63, and 4 was 112. Well, 28 minus 7 is 21. 63 minus 28 is 35. 112 minus 63 is 49. That's a difference of 14 and 14. Okay, so I have that common difference. Only it's a second difference, right? My first common difference is different, but my second common difference is the same. So what's really happening up here? Let's take a look at these guys. Well, if I kind of look at this in terms of, okay, so my size is 1. So 1 box, I have 1, 2, 3, 4, 5, 6, 7. I have 7 times the 1 box, right? Well, here, if I go by a 2 by 2 box, so 2 by 2, I have 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. I have 7 of my 2 times 2 boxes, right? I guess this would be a 1 by 1 to be consistent. Well, in the size 3, I have a 3 by 3 box, and I also have 4, 5, 6, 7. So I have 7 of my 3 times 3 boxes, right? What am I really doing here? Well, I'm taking, get a button. This is really my in, right? It's my size. So 7 times n is the same thing as 7n squared. So my explicit formula, scroll down, f of n equals 7n squared. I have 7 of my size squared boxes. Now, if I go to look for my recursive formula, that one's a little different in that I want to see what I've done to my previous one for each one. So my previous here is a 1 box. So if I put my 1 by 1 in here, I've thrown in 3 boxes. So it's basically the one box plus 3 over and over, right? I've added 3 to it. Here, my previous was a 2 by 2. Here I've added 5. So here I add 3, here I've had 5. This one I'm probably going to add 7. So I'm adding, if I'm adding 3, adding 5, adding 7, that's a difference of 2, right? Which we'd say is a 2 in, um, and I'm taking away, I don't have any on this first one, right? Minus 1. And let's see if that works. So I have 1. So 1 times 2 minus 1 is 1. Okay, that puts me back with 1. I'm trying to get what's in the blue right here. So these guys right in here. So if I put a 2 in here, 2 times 2 is 4 minus 1 gets me 3. I've added 3. Here, if I have a 3, 3 times 2 is 6, minus 1 is 5. So this is what I'm adding each time. So to do my recursive, it's a little more complicated. I'm going to do f of 1, I started with 7, then f of n minus, oh, nope, f of n equals my previous term, f of n minus 1, plus 2n minus 1. And I have 7 of those, right? I'm doing I'm doing that to 7 boxes. So I'm going up here. I'm not just doing it to this one box. I'm doing it 7 times. 7 times in here. So I have to do this 7 times. So the first one I'm adding 3, but I'm really adding 3, 6, 9, 12, 15, 18, 21. I'm actually adding 21 because I have 7 of these boxes in here. So that's how we come up with a recursive one for that. A little more complicated with these quadratic ones. So it says compare the models you developed for the first set of logos and the second set of logos. In what ways are they similar and what ways are they different? So here's where we're going to set up kind of a table so that we can see, really just kind of see how these are comparable. So we know that kind of what we're comparing here. I'm going to go ahead and, you know what, let me draw a table. Make it plenty big. And let's do 1, 2, 3, 4, 5. Let's do 6 layers in here. Oh, wish I could draw these a little better control over these guys. We'll just do some lines. So I need 6 spaces in here. So we'll just oh, I like how they tell me when it's a straight line, basically. Oh, too high. Undo. And then a couple more. You can probably draw this much faster than me because I have to do it this way. And then let's do, need to do three columns here. It's kind of a sloppy table, but that's all right. Okay, so basically we're going to compare linear and quadratic. So linear we've done doing all sorts of times. Quadratic are the new ones we're introducing with this chapter. this module. So here, let's talk about the rate of change, right? So it's kind of like our slope. So here, our slope is constant, right? It's always going add 2, add 2, add 2, add 5, add 5, add 5. Quadratic, though, we've noticed, is linear because the slope has that constant. So if you look up here, the first rate of change is not constant, but the second one is. So that means the slope actually has a linear rate of change. It has the slope. The slope has the slope. That makes sense. Um, okay, here, let's talk about the graphs. So linear is a line, quadratic is a parabola. So remember, the parabola is when that curve, draw it over here, we've got that curve going on like this. So far, we've only talked about positives, so hasn't really come into play. We've only seen half the curve. All right, equation. Let's talk about the equation next. Compare and contrast these. The linear's equation, highest powered term is x, right? And it's just an x, 2x plus 3, 5x minus 1. Here, the highest powered term is x squared, right? Oh, you know what? I can't probably do the equation in here. It's all right. We'll just do this guy. Is x squared. So we have an exponent in this one, but it's not the same as exponential. Exponential has the x as the exponent. Here we have a variable to an exponent. So slightly different. Okay, so the table, let's compare their tables. The table, when we were looking through, the first difference is constant. And if we go back up to the top here, here is our first difference, and we already had that common plus 5. Whereas a quadratic, it's not the first one that's the same, it's the second one, which means first difference is linear, second is constant. So we have to go in twice. We basically keep going until we find one that is um, constant. So then if we look at the diagrams, so like our pictures, if we look at our picture, this one up here really is just kind of going in one dimension, right? I mean, we basically add one on each end and call it good. Whereas in this one here, we not only got longer, but we also got thicker. So this little spot, he didn't just grow one direction because here above, he just kind of went out, right? He went one longer here, one lower there. He just kind of grew by one. Here we're doubling. We've got two down now, and we're growing out this way. So there's more than one thing going on here. So this one grows in length or one dimension. You just kind of went one direction with it. Whereas in a quadratic, grows in length and width, so two dimensions, which um, which makes a difference, which makes it why it's doubling. We have to do the square because it's a multiply in there. So, this is a good table to keep handy so that you have this information with you. Um, Otherwise, that's it for this lesson. Thanks for joining us. We'll see you next time.